Hi, Surya.
Hi, can you hear me?
Yeah. Did you
Yeah,
start
okay.
the meeting?
I mean, like, well, I mean, I don't know. I just shared
Open.
the screen and so on. But yeah. Hi, how are
Okay.
you?
So I'm fine. So you are first person here, huh?
Yeah.
Okay. How's life there actually? It is your
Uh,
final year, no?
yeah. I mean, I should have graduated last year, but yeah.
Okay. When did you move to US?
Somewhere 14, 15. Yeah.
In 13, you were visiting Munshi. At that time, I was at TFR.
Oh,
I
yeah,
saw
yeah,
it.
yeah,
Remember
yeah,
me.
yeah, yeah.
So are you in touch with Munshi also?
No, actually, I didn't talk to him for a long time. But yeah. I guess, yeah, he has been. Yeah, I should probably talk to him sometime. I haven't been
We should
thinking of
not
this problem.
record these things, right?
Oh,
Why we started recording?
I don't know. It automatically started. Yeah. So I'm going to talk about Klein quartic, some arithmetic aspects of Klein quartic. So just stop me if you have any questions. Just feel free to stop me in between, and we can like discuss any uh, uh, issues. So I'll present some arithmetic aspects, but maybe if you have time, we should probably discuss. Okay, what explicitly can be computed or other issues regarding these Klein quartic, for instance. Okay, so most of the content is taken from the survey article by Elkis in the uh, publication called Eightfold Way. Right? So the other articles in the same publication on Klein quartic. So for instance, there's the original article of Klein doing like some introducing and computing some stuff about the Klein quartic. Okay, and there
Why it is
are
called eightfold way?
uh,
This is some special conference on the Klein quartic itself, right?
yeah. So why? Okay, I'm not sure about that, but yeah,
Okay, I think there
yeah,
is
it
eight
should.
has some connection.
Yeah, it should be probably related to the symmetry, I guess. But okay, we'll see. Yeah. Um, okay. So again, I'll quickly describe. So in Bram's talk, we have actually seen. So different perspectives about Klein quartic. It's important to have all these perspectives. For instance, it can be seen as an algebraic curve. It has a structure of a Riemann surface. It's an hyperbolic surface, and it can be seen in terms of the tessellations on the hyperbolic surface and the hyperbolic plane. And it has a structure of a modular curve, and it's also something called a Shimura curve. So there are all these perspectives.
It can have a both structure, modular and similar both.
Yeah. We'll see. I'll probably talk about it in the end of So it has all these structures, and somehow it's important to see things from all these perspectives, see how they're related. So ideas from one perspective might help you to see things from other perspective. For instance, it might be easier to compute something just knowing some ideas. Like if you see it from the perspective of tessellations of hyperbolic surfaces, some facts might be easy to understand. Uh, it might be slightly harder to like prove the same facts purely from a different perspective. For instance, it might be harder to prove some fact just from algebraic perspective, but if you know that it's the same curve coming from hyperbolic surfaces or tessellations, it might be easier. Okay, so it's important to like keep all these perspectives together, understand how they're related, and try to move from one perspective to the other. So I'll okay, so I'll quickly talk about the hyperbolic perspective. Um, it's so the curve basically we can think of it as being made of 24 heptagons. Okay, so and 3 heptagons meeting at a single point. Okay, so there are 3 heptagons meeting at a single point, and 24 of them. Is the screen stuck? Can you see what I was?
The drawing, we cannot see the drawing.
Oh yeah, so I don't know
You are
what
drawing
happened.
at some other page, right?
Yeah.
Hmm.
So I don't know what happened.
You have to stop it and then do that.
Okay, so yeah. Yeah. So from the hyperbolic perspective, it's so you can think of the surface being made of 24 heptagons, and um, so and the 24 heptagons, every three of those 24 heptagons meet at a single point. So those and these heptagons form a tiling of the hyperbolic plane. Okay, so that's one perspective. That so if you just it's a completely symmetric surface with these 24 heptagons. Okay, just you have to just restrict to 24 of them, and rest of them are the same numbers which have the same number. So you number them by 1 to 24, and any other heptagon which has the same number is considered the same. So it's you're quotienting out this tiling such that you only have 24 heptagons. Okay. So from this perspective of 24 heptagons, there are lot of features of this curve that you can see. For instance, there are symmetries. So all the 24 heptagons, it's not apparent from this picture, but all the 24 heptagons are the same, are equivalent. So there's a symmetry relating all the 24 heptagons, and there is another symmetry that relates like each so you can rotate an heptagon and get like you can see a seven-fold symmetry. So there's 24 fold symmetry coming from moving from one heptagon to the other heptagon, and there's a seven-fold symmetry that comes from rotating the heptagons. So in total, you have 24 times 7 symmetries. If you consider just the orientation preserving symmetries. So it's easy to remember. It's 24/7. So 24 times 7 symmetries. So the size of this is 168. So just from this perspective, it's easy to see that the automorphisms of this surface are 168 in number. So, and we can explicitly and once okay. So there are 168 of automorphisms, and also like if so, I didn't tell you how you get to this explicit numbering. So if you figure out that, yeah, so like this is the way to number and like quotient out. So you have completely explicit surface, this explicit tiling, and then you can figure out what are the automorphisms. So there are 168 of them, but by just looking at the styling, you can figure out what is exactly the group of automorphisms. Okay, so so that's one perspective, and another perspective which kind of relates. Okay, I don't know. Can you see? I don't think you can see anything I'm writing, right? Hello?
You cannot see writing.
Tiling. Yeah, so
slide
I don't know.
4 of your whole slide. Slide number 4 is visible, that's all.
Yeah, that's, I don't know why. Okay, so give me a second. It's getting stuck. Sorry, I didn't use the setup for some time, I guess. Yeah. So you can see that there are 24 times 7 symmetries from this picture. So the picture with heptagons. And then there's another tiling. So those heptagons can be tiled further using these 2, 3, 7 triangles. So you can tile it with 36 such triangles, and the symmetries are the orientation. So if you don't care about the orientation, every triangle can go to any other triangle. So there are 336 triangles. So there are 336 symmetries, but if you only restrict to the orientation preserving symmetries, you get half of them. So 168. Okay. So that also kind of tells you the relation to the triangle group with 237. Okay. So okay. So and yeah, so another perspective to like for instance to understand the surface is that you can consider this 14 in this tiling. You can consider the fundamental domain of the surface is this particular 14 gon. Okay, so this exactly determines. So with some identifications, this 14 gone determines the surface. So for instance, you have to identify. So identifications are given here. So you have to compute and figure out what identifications work out to give you this particular surface with the symmetries I was talking about. So any questions about the tiling picture? It's just so there. One way to look at it is in terms of the heptagons, and there is the heptagons can be further refined to see these 2, 3, 7 triangles. So that's the tiling picture, and it helps you to see certain features. For instance, you can see that there is a symmetry of order 7 that fixes each vertex, and it rotates the whole like for instance, if you rotate this tiling, there's the order 7 symmetry. So fixing order 7 symmetry. Yeah. Fixing vertices. So there are other symmetries that you can see. For instance, so vertices are some important objects. You can also see that okay, so these vertices are the centers of the faces of the heptagons. There's some other, like the vertices of the heptagon, they are also important. So they correspond to some order 3 they are fixed points, order 3 symmetries, right? So when you rotate about, so there are 3 heptagons, you can rotate about those centers, these vertices, and you get some order 3 symmetries. And then about the sides, if you can like kind of map between this red and blue. So these red and blue, so switch those triangles, that gives you a symmetry of order 2 with midpoints of the sides. So there are these special points which are midpoints of the faces, midpoints of the sides, and midpoints and the vertices. So each of them have different order when under the symmetries. The midpoints of the faces are fixed by order 7 symmetry. The vertices are fixed by order 3 symmetry, and this midpoints of the sides are fixed by an order 2 symmetry. Okay, so these features are quite easily seen from this picture. So that's fun. So we'll use that in the later thing. So, but is that clear first?
Yeah, clear to me, Devatam. You have any doubt?
Yeah. So it just purely from looking at this tiling, we can figure out some aspects of the symmetries which are quite apparent. Okay. So that's the first idea. And then so I didn't tell you what surface you get, right? So so you have this 14 gone, and after identifications, you get some surface. In fact, you get a genus 3 surface. Okay. Can you see? Sorry?
I was asking if you have any doubts so far.
Oh, no, it's okay.
Okay.
Yeah. Okay, so you get this genus 3 surface when you actually do this identification. So I'll try to, after the talk, I'll try to show like a video which actually shows you how to like fold this 14 gone into this 3-hole torus. Okay, so there's a nice video which actually shows how to do the folding and show you that you actually get like a donut with the 3 holes. But you can compute it explicitly if you just from certain things, just knowing the tiling, like this triangulation, you can figure out the genus. For instance, so if you have, so we can see that. So can you tell me number? So if you just look at it in terms of the tiling by the heptagons, there are 24 heptagons. So can you tell me the number of vertices and edges? Right. So each heptagon has 7 vertices, but like each vertex is shared by three heptagons. Right. Similarly, each heptagon has 7 edges, but each edge is shared by 2 heptagons. So the number, so in the heptagonal tiling, you can see that these are number of vertices, these are edges, these are faces. So V turns out to be 56. E turns out to be 84, and F turns out to be 24. Okay, so from this you can compute that the genus is 3. Okay, is that clear? Right? Just
Yeah.
So also these numbers are quite important. We'll see these numbers again. So the number of faces or the face centers are 24, number of vertices are 56, and the number of edges or edge centers which are exactly 84. And we saw that they correspond to the special points on the surface, and somehow they are they really correspond to some, even from other perspectives, these are some really special points. Okay. So okay, so that's just the perspective of hyperbolic tiling tells you a lot about the surface already. So once you have the surface, you can just like once you have that tiling and the identifications, we can explicitly figure out what the group is, right? It just, so we have to figure out what transformations. So you have all these transformations, and you have to figure out what are the relations between the transformations. So one way to so if you just figure, it's a finite computation, okay? So if you just do that, somehow you can do it in many ways. One way to do, if you write down the relations between all these generators, you get a group of
S is the reflection and T is rotation.
So so T corresponds to this order sum rotation. S is not really the reflection. It is some, so this order 2 element. So it takes you, so it maps this element to this element. So it's kind of a reflection. It's not purely
Okay.
So yeah, it's kind of a reflection, but yes. So and it so you can see that those elements and with some extra relations generate the group. But the interesting thing is that, so we have this explicit group, and we can, it's a group of 168 elements. You can figure out, you can look into like maybe some tables and list of groups, and you can see that the group is exactly PSL to F7, or it's isomorphic to this GL3F2. Okay, so this group that comes up from the symmetries turns out to be related to some matrices, and it can be related to matrices 2x2 matrices in the finite field over 7 elements, or it can be related to 3x3 matrices in finite field over 2 elements. It's kind of the fact that these two, okay, first is that fact that our group is equal to any of this group is something surprising, and also the fact that these two matrix groups are equal, that's also surprising. So this is an exceptional isomorphism. You don't expect some isomorphisms like this in general. Okay, so what do you mean by PSL to F7? So it just, you take the matrices A, B, C, D, and such that over the finite field with 7 elements, so that the determinant is 1. That corresponds to SL to F7. And if you mod out by plus or minus identity, you get PSL to F7. Okay, so that's a way to see what the symmetries are.
It should be AD minus BC.
Yes, sorry. Oh, okay. Thanks. Okay. So then, so that's the presentation of the group, and so you can see that PSL to F7 can also be seen as a quotient of gamma 1 modulo this group gamma 7. So we have seen these groups. So gamma 1 is PSL to Z, and gamma 7 is the subset of elements which are identity mod 7. Okay, so ABCD is just identity mod 7. Okay, so if you quotient out from our SL to Z such matrices, you're left with this group PSL to F7. So this already tells you that there's a relation to the modular curve, but yeah, we'll come back to it later. So so right now I'm just saying, from the tilings and so on, we can figure out what the group is, and then and the group, you can see that the group is in fact equal to some few other groups like PSL to F7 and GL3F2. And this PSL to F7 is exactly gamma 1 mod gamma 7. Okay, so all these groups are the same isomorphic groups, and they have 168 elements. Okay, so this is the starting point to get into arithmetic. So So looking at the hyperbolic picture, we got this group, and now we want to understand some what is this group basically. So let's see. So way to understand the group is to understand the representations of the group, right? So there are 6 conjugacy classes in this group. So that will give you 6 irreducible representations. Okay, so you can compute this explicitly. I haven't done it myself. I think Magma. So we should try to see how to like make computers compute these things. So I think Magma has an inbuilt system to actually compute like irreducible representations. But yeah, so but our symmetry group has these 6 irreducible representations. You can see that the dimensions of the group are the representations are 1, 3, 3. 6, 7, and 8. Okay, and these representations, these are the characters, but okay. So these representations are dual representations. This 3-dimensional representation, and this alpha here is related to exponential 2 pi I7. This 7th root of unity. It's this quadratic integer. Okay. So somehow the representations are not really defined over. So I mean, a priori they can be defined over complex numbers, but they are defined over this field containing this element alpha. Okay. So I mean, I haven't written down the representations. These are just the characters, but you can also just take the generators and see where they are mapped to. So they are mapping to. So the matrices that you map your group to are in like our matrices over this field, this imaginary quadratic field Q alpha. Okay, so that's the representation theory of the group. So we are interested in this particular these 2 representations in particular. So I heard something. Sorry.
Go ahead.
Yeah. So that's yeah, you can, I mean, you can just compute this with hand. It's just take the regular representation and then split into irreducibles, and you'll see that these are it's composed of these representations with some multiplicities.
How you are bringing this field here?
Sorry?
How you are bringing this field here?
This field?
Huh?
Oh, so I'm saying the character. So for instance, element G is mapped to some matrix, right? So for instance, you can think of each representation is like mapping G to a matrix, and I'm saying this matrix elements are defined not just any arbitrary numbers, but they are these defined over these field. Okay. So for instance, you can see that the trace, these are traces, right? So the some traces of some elements are in fact this alpha and alpha bar. Okay. So I mean, I didn't write.
These are the representations of complex numbers.
Yeah.
So, but your previous descriptions that shows the representations over F7.
Oh yeah. That's also true. Yeah, there are representations over F7 and F2. We'll see that. In fact, yeah. So that okay. So so it's not easy to see from F7 to how they are related to complex stuff, but so from once you have this complex description, like these representations, we can see that by reducing mod, like these, because they're not just any complex stuff, they are defined over some number fields. We can reduce mod 2 in the sense that mod some prime ideals above 2, and we actually get these 2 groups that way. Like if you reduce mod 7 prime which divides 7, you get this group. If you reduce mod prime above 2, you get this group. Is that?
So so you are saying from the complex representations you can read the representations over F7?
Oh no, that's not what I'm saying. I'm saying those particular representations can be read. Those particular representations can be read from.
Another interesting thing could be that you see the representations over rational numbers.
Oh, yeah. So these 3 are the representations over rational numbers. They're not like except these.
No, I'm saying that you compute the irreducible representations over rational numbers.
And
now this is the trace field is not the field of definition.
Oh, yeah.
Yeah, but
Yeah.
I don't think that issue arises here about the Schur index. Schur index issue does not arise here. I think, yeah.
Yeah.
Anyway.
Yeah. So there's a lot of So there. Yeah. So we can. Yeah. So somehow, so one aspect of understanding this whole curve and this is to really understand a lot of features of the representations. But but yeah. So let's just focus on this particular two representations which are dual to each other. So they are three-dimensional representations. Okay. Okay, again, something happened. I don't know if it's my computer or iPad or okay. Okay, so we saw that there are these three-dimensional representations, right? So we can think of, so if you, hello, sorry. Yeah, so you have these three-dimensional representations, and we can think of just if it's a just give some coordinates x, y, z on the representation, and then we can look at, so, and there's a representation of the group, and then we can ask what are the polynomials in x, y, z that are invariant under this representation, okay, under this group action. So you can see that, so this is part of invariant theory, or like Hilbert's classical invariant theory. So you can explicitly compute what are the invariant polynomials of this representations. In fact, all the invariant polynomials are generated by some 4 candidates: phi4, phi6, phi14, and phi21. And out of them, these phi4, phi6, and phi14 are algebraically independent. So they're independent polynomials. And this last phi21 square can be written in terms of rest of the first 3. So this is also.
Are there programs to compute?
Yeah. There are programs to compute this, actually. Like I'm not sure how these people did it, but yeah, there are programs. This is also a finite computation. There is Hilbert. I think the Hilbert's proof itself gives you a finite, like tells you that it's a finite computation, like maybe with some modifications, and then I think there are programs to do this, like to just print out the representations. Yeah, I haven't done it myself. Yeah, I want, like, maybe we should try to figure that out sometime during the course, actually.
Oh, no, or otherwise the programs are there. Which programs do this?
Oh, yeah. So yeah, there are people. Sometime back I've seen that there are people like working on really intricate algorithms related to representations for different groups, but some kind of their relation to modular forms and so on. But I guess So I think it's in Magma. I don't think it's in Sage. I've seen it. I'm slightly familiar with Sage. I didn't see the implementation in Sage, but Magma might have a way to just print out these things. So we have to figure out how to present the group G to them, maybe, and then see how and the representation, and then see if it prints out these polynomials. Okay. So, but it's a finite computation, but
how about this program GAP?
Oh yeah. So I've heard the GAP. I guess this also has. I haven't used it myself, but yeah. We should definitely try to look. I'm interested in explicitly computing things. Maybe we should all look into how to do these things with these programs. Yeah. So but okay. So so these invariant polynomials, and we can compute. So one invariant polynomial is this phi4, which is x cube y, y cube z, and z cube x. Okay, so this is the polynomial. So this is an important polynomial. In fact, we will see that the Klein quartic can be defined by this equation, in the sense that if you equate this equation to 0, right? So you'll in the complex, think of it, it's a homogeneous equation. So in the projective 2 space over complex numbers, so it defines a curve, and that is a algebraic model for the Klein quartic. Okay. Questions on that? So from this representation, we get these polynomials, and just equating this first polynomial to 0 will tell you, and that's an algebraic curve, projective algebraic curve, and that is a model for the curve. Like that's you can think of it. It already gives you some Riemann surface structure. It also gives you it's also a projective algebraic curve. So once you have that equation. Oh, okay. Any questions on this?
Are there any interpretations of 5.6 and 5.14?
Oh yeah. So So
5.21?
I'll talk about it. Yeah. So 5.6. Okay. I mean, you can write explicitly those polynomials, but 5.6 is the Hessian of this phi4. Okay. And 5.14 is also kind of a Hessian related to 5.4 and 5.4. Like it's not really Hessian. It's some super differential. Yeah. It's related to these 5.4 and 5.6 with some derivatives. And phi21 is a Jacobian of all these previous guys, phi6 and phi21. Okay. Okay. So they are related to, yeah, you can. So once you have this curve, you can see that these are related to some geometry of that curve. Like phi4 equals 0. So all the rest of these things are, this Hessian corresponds to the inflection points on the curve, and these also correspond to some interesting points on the curve. Okay, so yeah, it's not like in general. Okay, so if you know one invariant, we can always compute such expressions like this, and it will be an invariant of that. If you have one invariant polynomial, so and you can compute expressions like this, some determinants. In general, Cayley has more expressions, generalized determinant expressions, and all of them will be invariants of our group action. But in our case, somehow just these generate all the invariants. Okay, so coming back to your, okay, so I've already so I mean, I guess this is to just explain why you have relations to SL to F7 and GL3 F2. Okay, I guess I'll skip this. It's just you have these matrices, and and they're defined over some number fields. If you reduce modulo some primes, you get these isomorphisms. So if the same matrices reduce modulo primes above 2, you get isomorphism to GL3 F2, and they reduce mod primes above 7, you get an isomorphism to GL2 F7. Okay, so if you want, that explains this exceptional isomorphism. In general, it's a principle that somehow if there are exceptional isomorphisms, they are seen by reductions mod different primes of some, like here these are some representations, but in general of lattices. So you see a lot of interesting, very structured lattice, and you reduce mod primes, you the isometries of those lattice.
This V is a three-dimensional complex vector space.
Oh yeah. So yeah, so this is okay. I have to explain where you're getting GL2. You have to remove out some one-dimensional space. This is, I didn't write it down properly here, but yeah, V is the three-dimensional representation.
But when you say lattice, you mean the integral lattice in that?
Yeah.
But will that be invariant under the group action?
Oh, no. Oh, okay. It's not apparent from like just from the definition without any comments. But yeah, you can find the lattice which is invariant under the group action.
Yeah. Okay.
Yeah. Okay. So, but anyway, that is to just explain the exceptional isomorphism, if you guys want. But okay, so let me come back to this equation. This is the phi4, which is the invariant polynomial of that representation, and that is a curve, and the curve itself represents, if you take the complex points, it's a nice curve. You can see that it's a smooth and genus 3 curve, and it will have all the so this is a completely different model. We've from the tessellations and hyperbolic plane, we've moved to some algebraic world. But you can see all these features. It's the same curve. So we should try to look at how it's important to kind of relate how all these pictures. So I'll try to kind of say the relation later, but like I'm saying, this also is a model for our curve, and you can see that it's smooth. It's of genus 3. So given this equation, you can explicitly compute the genus. So it's a smooth curve. It's of degree 4. So that will already tell you what the genus is. And the symmetries. The symmetries are basically the representation symmetries, right? So we know for G goes to some matrix, and the matrix acts on these X, Y, and Z. That gives you the symmetries. Yeah, so this 168, as we have seen in Bram's talk, is like the maximum number of symmetries that any genus 3 curve can have. It's called the Hurwitz bound. So for genus G, you can have at most 84 times G minus 1. Okay, so and the statement about, okay, so this is a genus 3 curve. There are 2 general families of genus 3 curves. One are hyperelliptic curves, but this curve is not the hyperelliptic curve. Okay. Okay, so these are some.
When you consider lattice in 3-dimensional complex vector space, so you are considering the lattice is Z to the 6 or Z to the 3?
So it's just Z. I mean, it just so you take a proper like some basis, the 3-dimensional basis, and the integer combinations of them. Yeah. So it's just 3-dimensional. Yeah.
But over the complex numbers. But so you are taking the integral.
Yeah, integral
combinations of the basis.
Yeah, of the basis. Yeah, not as a lattice inside that 6-dimensional space. Yeah.
Okay. All right.
Yeah. Okay. So any questions about this? From a complicated, like from looking at the representation theory, we somehow found a polynomial which has all the symmetries of the Klein quartic, and we can explicitly compute. So for instance, like I'm claiming that they're smooth and genus 3. So these features were easy from the other perspective, but now we have to do some computation. So how do you show that it is smooth? Okay, these are some pictures. So if you just take on the Z equals 1, like just plug Z equals 1, you get some points like this. If you plug X plus Y plus Z equals 1, you get some points like this. But okay, so why is it smooth? So we have to explain the different ways to think about it. So we can explicitly compute so the conditions for non-smoothness. For instance, that X cube Y, Y cube Z plus Z cube X equals 0 should be satisfied at a point, and the derivatives all should be equal to 0. If there is a singular point, so these conditions have to be satisfied, and we can see that so these are polynomial equations. So I've actually computed this, and so you can do this in Sage. So these are polynomial equations, and Sage tells you that the only you can plug it into Sage, and you can see that the only solution will be X equal Y equals 0, and that's not allowed. It's you are in the projective space. Is that clear? Right. So the point is non-singular if all these derivatives are equal to 0. So that's one way to see that it's smooth. Or another way is that so this is a degree 4 curve. We can see that there are at most I guess 3 singular points in general, and the singular points have to go to the singular points. So that means that under the actions of the automorphism of the all the actions of the group symmetries, but then our group doesn't have a subgroup of index like the maximum, like the maximal subgroup that you have, the biggest subgroup that you have inside our group is, I think, of index 9 or something. So that's why you can't have the singular points. Is that argument clear? Okay. This is quite explicit. This is using this action of the group. You can see that there are only at most three singular points, but the group action has to take the singular points to themselves. But then we don't have a index 3 or like subgroup inside to have, because if you only have three singular points and under the group action it's preserved, each point has to be fixed by a group of size at least 1/3, and we don't have such a big subgroup.
What is this formula? Only three singular points? Is this some algebraic geometry formula?
Yeah. I think it's some algebraic. Okay, I mean I don't even need 3 here. Like for instance, here some Bezout's theorem kind of like this is a degree 4 equation and a degree 3 equation. Some Bezout's theorem kind of stuff will give you, so some application. It comes from some algebraic geometry bounds that the maximum like for this particular degrees and so on. I mean is that okay? I mean I'm just saying we can, so this is of degree 4 and this is of degree 3. That tells you there are at most 12 points, but maybe you can do better. So in general I think you can have some d-1 choose 2 singular points if you have degree d plane curve. But anyway, that's is that clear? So either you can argue by a group action and the structure of our group that it has no singular points, or you can explicitly compute the derivatives and set it equal to 0 and then see what are the solutions, and you can see that x equals y.
So this is the formula for d-1 choose 2 are the maximum number of singular points
on a degree d plane curve,
counting with counting with multiplicities.
Okay, so any questions on this? So over complex numbers, these are the only solutions that we get, hence it's a smooth curve. But this explicit computation also kind of is better in my perspective. Kind of it tells you, for instance, if you do the same computation over like some other so if you think of this curve over f7, if you do the same computation, you can see that there are other solutions. Okay. So for instance, f7 has some singular points. Okay, so genus 3. So we have already seen that it's genus 3 from from our Euler characteristic computation, but you can also like just explicitly from this description of that it's a degree 4 smooth curve. It already tells you that it has to be of it already tells you that it has to be genus 3. So this for a degree, if it's smooth, then the genus exactly has to be this. Or you can write down some explicit maps from xyz to xz and compute using some Riemann-Hurwitz formula, and you can see that the genus is 3. So from the perspective of algebraic curve, also you can do the same computations. Okay, but it was quite easy to do it from the perspective of this hyperbolic tessellations. Okay, so this is the projective curve. That means we're considering xyz as the homogeneous, like if you scale xyz by a scalar, you get back the same point. So you are in the projective coordinates. But if you actually just set z equals 1 and you look at the affine part of the curve, then you see that there are 24 points missing. Okay, so there are 24 points at infinity on this curve at those that satisfy z equals 0. Okay, so that's called the affine part of the curve, which misses these 24 points. And these 24 points exactly correspond to the centers of the 24 heptagons. Okay, so these numbers 24, 56, and 84 keep appearing again and again. So these cusps or these infinite points are exactly these centers of heptagons. Questions on this?
No.
Yeah. Okay. So as I said, so this is the representation explicitly written in terms of the like some generators. Okay, so these are some generators of the matrix of the group, and these are like these are some quantities. The representation is explicitly written. So okay, so I guess I already talked about it. Right? So you can see that all of them are some expressions related to e to the this 2 pi over 7. So they're defined over that field, and you can see the yeah. Okay, so again, so let's get back. So we have this equation, and I said from the perspective of hyperbolic stuff, we saw some special points, but what are the special points from this perspective, right? So from this perspective, the special points are the points, so there's an orbit of, so in general, so the group is acting on this curve. So most of the orbits of the are of size 168, right? Most of the orbits are just, each point is not at all fixed, and you get an orbit of 168. But there are some special orbits. There are some few special orbits. For instance, there's an orbit of 24 points, which corresponds to these centers of the faces. And here in the algebraic perspective, they exactly correspond to inflection points. Okay, so inflection points are the zeros of the Hessian, and so hence they're zeros of this second invariant polynomial. Okay, so these special points satisfy this first invariant equal to 0, and also the second invariant equals 0. And there are 56 other special points which satisfy this third invariant equal to 0, phi 14 equal to 0, and phi 4 equal to 0. And then there are 81 points which satisfy phi 21 equals 0 and phi 4 equals 0. Okay, so there are some special points coming purely from algebra, but they correspond exactly to 24 face centers, 56 vertices, and 84 edge centers.
This subgroup is not normal, right?
Which subgroup?
You said it is fixed by a subgroup of order 7.
Yeah, I don't. Yeah, I'm not. Yeah, maybe. Yeah, maybe it's not normal. Yeah.
No,
Why are you saying?
PSL to Z mod 7 is simple, so there is no normal subgroup.
Oh yeah. Okay.
So 24
yeah.
maybe it has something to do with the conjugacy classes of elements of order 7.
Oh yeah. So you're asking why? Oh, okay. So from the perspective of the group, how do you see these 24 points? Yeah, it's like let's see. So maybe we can see here.
Maybe there are 24 conjugacy classes of
order 7
subgroups.
Yeah. I should. Yeah, probably we can. Yeah. You can see it from the purely from the group perspective, and I have to look at it. I'm not sure, but yeah. Is that clear? So these special points are purely given in terms of algebra now, just intersections of these algebraic equations, and they, for instance, have geometric significance. For instance, because phi 6 is the Hessian of phi 4, they are exactly the inflection points. And similarly, you can see that these 56 points correspond to some things called bitangents, the points which have the same tangent. Right? There are 28 pairs of points which exactly have the same tangent passes through both the points. So there are 28 bitangents on that curve. And these 84 points, I'm not sure what the interpretation is. There's some other algebraic interpretation, geometric interpretation. Okay, so is that clear? So from the algebraic perspective, either you can think of them as this, the intersections of these polynomials. So our basic curve phi 4 equals 0 with this extra setting this other invariant polynomials equal to 0, and they have some algebraic geometric significance as inflection points or bitangents and so on. And these are exactly the special points from the perspective of the group action as well, and these in the sense that they are the only points which have some non-trivial post elements fixing them. Okay. Okay, so yeah, so let's see. There are, I guess, so yeah. Now I'm slightly moving to something else. Any questions till now?
No, go ahead.
Yeah. So let's see. So then there we can ask, of course, if we have this algebraic perspective, we have something about the geometry, but now we can ask other questions. Like for instance, we have this curve, what happens? And we have a group acting, and if you take a subgroup and if you take the quotient of the curve, what happens? So what kind of curves do you get? So in general, most of the quotients will be just will give you a genus 0 curve. But if you quotient by subgroups of, there are some subgroups of order 2, 3, and 4. If you quotient by those, you get a genus 1 curve. So for instance, if you take a order 3 subgroup, and if you quotient by the order 3 subgroup, you get a genus 1 curve, which is this elliptic curve. Okay. Okay, so this elliptic curve is a really important. It's important to really understand arithmetic of, like, if you want to understand some arithmetic aspects of chi, like arithmetic in the sense that something about integer or rational points on the curve x, this elliptic curve is really helpful. So we have this map from chi to chi mod h, which is this elliptic curve, and so which is basically obtained by quotienting with this order 3 subgroup, and so the features are in this map. When you quotient it out, the fixed points of h are the branch points, so they are not changed. And this elliptic curve has J invariant, an invariant of elliptic curve, which is minus 15 cube. And it also, this elliptic curve has also, it's not a typical elliptic curve. It has it has something called complex multiplication. So if you see in terms of the lattice corresponding to the elliptic curve, the lattice has a lot of structure in the sense that it corresponds to an ideal in this Z alpha. It's like the alpha is this quadratic integer that we saw. We can see that it is.
So it is by just order 3 or just order 2 and 4, we also get the elliptic curve of CM.
Oh, we also get order 2 and 4 also you get elliptic curves, but
with CM.
With CM, probably I have to think. I don't know about that. I have to think of it. Yeah. And then okay, so that's a quotient by order 3 subgroup. But if you can quotient by the entire group, right? For instance, you could just quotient by the entire order symmetries, then you get just a genus 0, and the explicit map between the quotient chi and chi mod. The quotient is just you take the points x, y, z, and you compute these polynomials, right? That's an
Bailey map.
Oh yeah, that's a Bailey map actually. Yeah. So we can see that it's. Did I write it somewhere? But yeah, so we should check. We can check that exactly the points corresponding to j equals 0, 1728, and infinity. There are some. Those are the only branching points. Okay, so these are some important. So you have a curve from. So you can, from the perspective of the group or the algebra, you have this interesting maps between the curve to some other objects. Okay.
Is the j related to the j function? J
it's related to the modular forms. It's a j function. Yeah. So you can see. Yeah. So if from a different model of chi, you get that this j is exactly the j function. Yeah.
So is this a j function?
Yeah, exactly. Yeah. Yeah.
This is the j function.
Yeah. So for instance, these phi's will correspond to some modular forms, and if like so I have to explain what x, y, z, and phi are. If I specialize those tell you what x, y, z, and phi are, then j will be exactly the modular function.
So in that modular function, these phi's will become those Einstein coefficients.
Yeah, they are Eisenstein series, and they are some modular forms. Yeah. So I'll show you hopefully like a few minutes. Okay. Okay, so any question?
That's another representation of J in terms of Eisenstein series, and this is a different representation, it seems.
Oh yeah. So these fees will be exactly those Eisenstein series. So these can be written in terms of these Eisenstein series and this Ramanujan delta modular form. So yeah. So I didn't understand the question exactly. So
so that J, the actual function, arises from that Eisenstein. The usual definition of J is in terms of those functions arising from the Eisenstein series. But this is a different representation.
Yeah. So the different representation in the sense that so this if a point on the curve, right? I'm calling it XYZ, right? But if this XYZ represent the tau, right? Like I didn't tell you what the correspondence between this tau on the hyperbolic plane and this XYZ. If you know the correspondence, it will exactly correspond to the J function. Is that right? So there is a relation. So I can see this XYZ as exactly coordinates corresponding to this tau, and then J will be the corresponding. If you move to those coordinates, J will be the J function. Yeah, is that? I'll show you. I have some stuff. I'll show it to you, I guess, in some time. Okay. So anyway, so these are from the curve. You have all these interesting maps. So I guess so now I'll show some actual real arithmetic application of that map. Okay. So you want to understand rational points in this curve. So this curve is of genus 3, right? So in general, it's really hard to understand rational points on a genus 3 curve, like how do you compute them and so on. But Falting's theorem is like it's something that tells you that there are finitely many number of rational points. Like it's not, we can't determine what those points and so on are, but you know that there are finitely many points. Okay, so that is Falting's theorem abstractly applied to this our curve. But in our case, with all this structure, we can explicitly determine, we don't need to apply Falting's theorem or anything. We can just explicitly show that there are finitely many points and we can determine the finite points. For instance, in fact, the only points on this satisfying this equation, rational points, are exactly 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, so how do you do that? So if you're arithmetic geometer, this is I guess a standard argument, but let's see. So you have this map from chi to ek, right? So this is a rational map in the sense, if you take a rational point on our curve, when you it maps to a rational point on this elliptic curve. So is that point clear? So we have this map, and it's defined by some rational polynomials. So if you take a rational point with rational entries on our curve, it will map to a rational point on this elliptic curve.
You are taking K is any number field, huh?
Oh no, this EK is this. It's just the notation of Wilkes. It's just K is our
notation of elliptic curve.
Oh yeah, but with this K is this field corresponding to Z alpha, O alpha, Q alpha. Yeah.
Okay.
Yeah, this particular elliptic curve. Okay. So we have this explicit map from our curve to this elliptic curve. So if you have rational points on this curve, just see what is the image of that rational point. That will be a point on that elliptic curve, and it will be a rational point on that elliptic curve. Is that clear? First the connect. So from our rational points on the curve, you can move to rational points on the elliptic curve.
Okay.
And then somehow rational points in elliptic curves are easier to handle. There are a lot of stuff that we don't know about them, but in some cases we can handle them. So for instance, by some standard very basic, I didn't write down the argument. It's a very basic elementary argument in the style of Fermat descent. So if you have a point satisfying this equation on this elliptic curve, we can show that by some series of manipulations, we can show that from a solution of some size, we can reduce the size of the solution. So right, you might have seen a very elementary number theory kind of argument. So in fancy terms, it's called the descent argument by a to isogeny, but it's basically take a point on that curve and by some series of manipulations show that you get another point with smaller coordinates, and that is this descent argument. It's in the style of Fermat's stuff. Okay, so if you do that, you can see that the only rational points on the curve are 0, 0, and the point at infinity. Okay, so we moved. So the only rational points on the elliptic curve are these specific points, and we saw that every rational point on our Klein quartic maps to these 2 points, because as I said, rational points map to rational points. So that means that to compute our all rational points, you have to just compute the pre-images of these points, and that's so we have the map. Once you have the map explicitly, we can just compute the pre-images.
You are running out of time, so maybe wind up in 10 minutes.
Oh yeah. I guess so this is like the main application of all this stuff, like arithmetic application in some sense. Okay, so is that is it clear, this argument? So somehow having this map to an elliptic curve and showing that showing that there are only 2 rational points on the elliptic curve automatically kind of shows that there are only finitely many rational points, and in fact you can compute the rational points on this curve.
Okay, so one kind of question is that if we have the way you computed the curve, algebraic curve from the symmetries, is there a general recipe and there is a general program to do that? Initially,
the programs,
the representation of the finite group and over the C, the way you did that table, and then you come up with that equation, right?
Yeah. So how do I get this? Oh, okay, yeah.
So means if we have knowing the symmetries of any other surface, Riemann surface or tessellation or triangle group.
Oh yeah. So you can get so you can get some invariant polynomials, right? But it's not clear that invariant polynomials. So I mean, for instance, this is one of those invariant polynomials. It's not clear like which invariant polynomial might define the curve, or I'm not. Yeah. Like I'm not sure like how much computation you is it like a finite computation or not, but we should we should probably think about it.
Yeah, maybe we should think about it. It is one of the kind of the program.
Let's try to discuss that.
Okay, go ahead.
Okay, so is this clear? So rational points, because of this map to the elliptic curve, are like can be easily found. Okay, so that's I didn't write down that argument, the descent argument. It's like just like it's something that Fermat would have done. Okay, and another application that almost immediately from what I said is that there are no solutions to the Fermat's last theorem for n equals 7. Okay, I mean Fermat's equation for n equals 7. How do you get that? So if you have a solution on this Fermat equation, right? So from that given a solution satisfying this Fermat equation, we can create a solution to our Klein quartic. So this is the map. Given if ABC satisfies this equation, this a cube C, we can compute and see that this satisfies right? Is that clear? So if ABC satisfies this equation, then these particular choice of numbers satisfy our Klein quartic equation. So so that automatically tells you that that there are no solutions to Fermat's last theorem, because the only solutions on the Klein quartic, rational solutions on the Klein quartic, are trivial solutions. So so that means that the only solutions that we of the Fermat's curve should also be trivial solutions. Okay, so this is one other application of the same arithmetic of the Klein quartic. Any questions on this?
No.
Yeah, so I guess there are so many other aspects. For instance, I don't know, like I'll skip this, so you can understand, you can try to compute things about this this
What
curve
you are
mod.
doing here?
Oh, this is, I'm just, yeah, you can just compute, take the curve, take mod, look at the curve modulo some over the finite fields, and you can compute something called the zeta function.
Okay.
Yeah. So yeah, and
Then
this is quite
zeta
explicit.
function.
Yeah, I did the like Sage gives you these numbers, and then I can compute this. Okay, you just need finitely, you don't need all the numbers. If you just compute, in this case, if you compute first numbers, you can just compute the zeta function over. Okay, so this is, and mod 7, I said the curve is singular. This is a singular point if you want, and there are other more. I'll skip that. Okay, so the thing is, this curve also, our Klein quartic can also be seen as the modular curve x7. Okay, so we've already seen in previous talks what this x7 is. So there is, it's just quotient of h by this group gamma 7 that gives you a surface with some cusps, in fact 24 cusps corresponding to those centers of the faces, or basically this infinite point. Okay, but they're not, so that's not really a compact surface. If you actually compactify that surface, we get this Klein quartic exactly. Okay, so x7 is so Klein quartic is exactly equal to this compactified surface, which is x7. Okay, so the reason it's related to arithmetic is because this xn in general parameterize elliptic curves. Okay, so I'll leave that. In fact, so the map natural. Sorry. Let me. Okay, I want to get to showing some those modular forms at least. Okay. Okay, so I'll leave this.
Can you continue the talk next Saturday?
Yeah, I mean, okay, yeah, I can continue. I have a lot of things to say, but yeah, okay, yeah, whatever you, yeah.
It's getting very interesting, and I think we need some rest.
Yeah. Oh yeah, okay.
Rest, and maybe we will come after 1 or 2 talks, because something will be talked about it. Like we take quark, we'll talk the generalities of it. General triangular modular curve. So after that, we can discuss in next month again.
Yeah. So, but okay. So then maybe I'll just show you those things that we were discussing about.
Yeah.
So let's see. So the thing is, so on the x7, right, on the modular curve, you can compute some modular forms given by these explicit Q series, or like, is that clear? So there are some expressions which are modular forms of weight 2. These are some functions on x7 with some symmetries corresponding to gamma 7, right? And I'm saying that those xyz explicitly satisfy this equation.
I see.
So if you take on x7, it's in the hyperbolic plane. So if you take these x's, y, and z are the specific modular forms, they satisfy this equation. So that's exactly the map from moving from this x7 to this curve. Is that okay? So that's the relation between the modular forms and or like this picture, algebraic picture, and this modular curve picture. So the relation can be seen in terms of these modular forms. Yeah, like the coordinate x will be exactly modular forms.
Okay.
Yeah.
So
okay. Yeah.
I'll keep discussing it even in next semester when we have to discuss examples on the modular forms and other things in the second semester.
Yeah.
We'll come back to it.
Yeah. Okay. Yeah. Yeah. Fine. I'll stop then. Then we can discuss. Yeah. Thank you.
Nice talk and nice presentation.
Yeah. Thank you. Yeah. Okay. So.
Okay. So send me the slide. I will post it if you allow me.
Which one?
Send me the slide and
we will... Yeah. Okay. Yeah. Sure.
Yeah. Thanks.
Yeah. Okay. Yeah. Thank you. Thanks a lot. Yeah. I'll see you. Bye.
Okay. See you then. Bye.
Yeah. See you.
Have a good day.
Yeah. Okay. Have a nice day. Bye. Yeah.
Thank you.